So please give attention, please, to Csongor Ferenczi.
Hey everyone. Hey everyone. My name is Csongor Ferenczi, and I'm an IT security specialist at Ukatemi. And in this presentation, I'm going to tell you a story about how we found a critical vulnerability in an industrial firewall. Why do we need industrial firewalls? Well, a lot of industrial appliances are simply not made to be secure, and thus they need protection. However, regular firewalls are not always suitable for this kind of job, since industrial environments pose special requirements such as wide temperature and humidity ranges, or special protocols that needs to be analyzed, and so on. In one of our projects at Ukatemi, we are working on creating a secure industrial firewall with Bolosys and the University of Szeged. And in order to make something better, first we have to evaluate the security measures of a few existing devices. And during this assessment, we are trying to find vulnerabilities, and our goal is to eventually gain root access on the device, dump the file system, and analyze the results. So how are we trying to do this? Well, we usually divide the penetration test into two sections, a hardware and a software-based test. During the hardware pen test, we try to gather information about the device, then open it and analyze how it works. We usually look for connectors and test points which can give us low-level access to the operation system. And if it is necessary, we can also desolder the flash and dump or extract the firmware from it. After we are finished with the hardware side, we focus on the software components, and we usually map the interfaces and the services, and we can then perform a black or gray box analysis. And if we have binaries, we can also do static or dynamic analysis on them. So the subject device, it was made in 2010. And while it can seem that it was a long time ago, industrial devices have longer lifespan than regular ones, so it is still not obsolete. The device can perform protocol analysis and packet filtering, and it has a configurator application which can be used to configure the device via USB or via the network. The device is a level 2 device, meaning that it has a MAC address, but it does not have an IP address, and in this context, it appears to be transparent to the rest of the network, so it's easily deployable. All right, so let's start off with the hardware side. Well, let's take a look at the outside. As you can see, there are two Ethernet connectors on the front, a serial connector, a USB port, a redundant power plug, some feedback LEDs, and another additional port. If we take the device apart, we can see that there are 3 PCBs inside, 2 holding the Ethernet connector itself, and 1 for the main board. The main board has several chips installed, including a system on a chip, 2 RAM chips, a flash chip, 2 Ethernet transceivers, a serial transceiver, and an FPGA. The FPGA is kind of weird to see because it's usually a costly component, but in this case they use it to physically disconnect the USB port from the CPU. So, can you see anything interesting on the pictures? If you sit close enough, perhaps you can. There is a connector on the bottom of the board next to the CPU. These kind of connectors are usually used for programming the board via JTAG, or they can provide low-level debugging, or sometimes even shell access via UART. While we managed to figure out the JTAG pinout, we unfortunately did not have a device which could communicate with this chipset, and we did not find a UART or other protocol on these pins, and since we had to keep the device operational, desoldering the flash chip was not an option, so we had to conclude the hardware side of the pen test at this point. So let's take a look at the software side. As I mentioned before, there is a USB port on the front of the device. This USB port can be used to fetch some diagnostic data from the device. Most of the data is encrypted. However, there are a few plain text files containing information, such as the firmware version or network statistics and so on. The USB port can also be used to deploy a configuration by generating one using the configurator. However, the configuration file is encrypted, so it is not really useful for us. On the other hand, if we configure the device via the network, we can create a packet capture, and we can see what's going on during the configuration. As it turns out, the configurator uses port knocking, meaning that it sends a magic packet containing a payload, or in this case, an encrypted payload, to the device, which in response opens a port for the sender, and then a secure shell communication gets established. But if they use SSH, could it be that the configurator is executing just plain old shell commands? Maybe, maybe not. Basically, at this point, we have two options. The first one is to break the port knocking, somehow get a hold of the SSH private key and log into the device. Or we can also modify the command that the configurator executes via the SSH. To achieve any of these, we first have to analyze how the configurator works. There are two analyzation methods, static and dynamic. During static analysis, we try to figure out how the program works without running it, for example, by disassembling or decompiling it and then looking at the instructions. While during dynamic analysis, we run the executable and analyze the contents of the memory, or we debug it and so on. The binary itself is 65 megabytes, which is large but not undoable. But unfortunately, IDA was unable to process it. And we dig into the configurator's files, looking for some clues why IDA may have got stuck. And we found a bunch of jar and other Java-related files. We also found a tool called JetVM, which, as it turns out, is a Java to native code compiler and an obfuscator. And unfortunately, there is no deobfuscator available for this tool, so we had to move to dynamic analysis. So, during the dynamic analysis, we started by creating a memory dump from the configurator while fetching the diagnostics from the device. After this, we analyzed the dump with bimwalk, strings, and other analysis tools. We found an interesting text called node diagnostics containing a lot more information than the one we fetched via the USB port. It reveals the firewall rules, the routing table, details about the connections, the script itself that creates the firewall rules, a list of the installed packages and the corresponding versions, log messages with more details than the one available in the configurator itself, a private key which got us excited, but unfortunately it is encrypted and we were unsuccessful decrypting it. And we also found an interesting path pointing to a shell script called node diagnostics. Could this be that this node diagnostics shell script is responsible for creating the text we are seeing? Well, if we look further, we find a list of running processes, which includes an entry where the node diagnostics path is passed to sh, which executes it in a new shell. And as you can see, this new shell is running as root. So let's search for this node diagnostics path in the memory. And if we stop the execution at the right moment, we can find it in plain text, as you can see. We can also find it in another location, saying executing command and the path itself. So we change the path to test, 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 which is an easily recognizable and searchable pattern. And after fetching the diagnostics, sure enough, we found the string saying executing command test, test, test. And not just that, but we also found a different string saying sh test, 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 not found, meaning that the device tried to run test, test, test as root. So at this point, we have arbitrary code execution. We can modify the node diagnostics path and run anything we want, basically. There are a few limitations, such as that only the standard error gets logged, the length of the command itself is limited, and the return length is also limited. However, we can deploy longer scripts via the USB port, and if we need, we can pipe the results into head or tail to get different segments of the output. So that's what we did. We inserted a pen drive and dumped the file system. To achieve this, first we had to figure out how the FPGA isolated the USB port from the CPU, because nothing was showing on in LS-USB. However, after finding the relevant script and undoing the magic, we had no more obstacles ahead of us. What we found are scripts, configuration files, custom binaries, public and private keys, including the config encryption key, although it is important to mention that the configuration encryption key is unique for every configuration. And of course, we also found a lot of answers to our questions and useful insights for the projects. So, what are the key takeaways? What did we learn? Well, first of all, security by obscurity is once again not the solution to protect resources. They thought that the device is secure, and we managed to exploit it. And remember that this device could be the barrier, the last barrier between critical infrastructure and an attacker. Secondly, it is also a good example why is it so important to penetration test your assets with experts, no matter whether it is a hardware device or a software solution. And finally, this is a friendly reminder to fix your mistakes, because we notified the manufacturer over a year ago and still got no answer from them. Yes, one can say that this is an architectural issue that's hard to fix, and exploiting it requires insider knowledge, but it is still a vulnerability and it needs to be fixed. So I thank you so much for your attention, and if you have questions, I can answer them now, and if I have, as I can see, I have a few minutes left, I can show you a demonstration about the attack in work.
Thank you, Csongor. Before the demonstration, does anybody have any question related to this presentation just now? Okay, if you do have anything, Csongor will be available around lunchtime or this afternoon. So, Csongor, please continue with your demo.
Thank you. All right, so what we are going to see is the output of the screen of the x64 debugger. I'm going to attach to the configurator application. and search for node diagnostics, for the node diagnostics string in the memory. And after I found it, I am going to modify it. And the command I'm going to inject is ls, so it is going to list the contents of the root folder itself. So after the modification, I go back to the configurator and fetch the diagnostics to execute the command I have just modified. And after it finished, I go back to the debugger. I search for the node diagnostic, the exit status string, which is always located before the result. And if I modify the contents to list it in a more readable format, you can see the contents of the root folder. Thank you.
Thank you, Csongor. Csongor's very first public presentation. Does anybody have anything to question or to add? Okay. Oh, yes, we do.
You said the firmware, the device was released in 2010. How many firmware releases has been since 2010, approximately, if you know?
I cannot give you an exact number, but I believe there are a few years have passed since they last released an update for this device.
Anybody with anything else? No? In which case, again, Csongor, thank you and congratulations.
Thanks.